Thank you for the introduction. I will just briefly introduce you because maybe many of you haven't heard about INL yet. So we're a research organization. We're an intergovernmental research laboratory focusing on nanotechnology, and we are located in Braga, which is the north of Portugal. So you can see here with the green dot on the screen. Basically we have a large clean room facility, and we have a state-of-the-art electron microscopy facility, which is located underground in a very noise-shielded environment. And so we are organized internally. We focus on 6.
Sorry, Pieter.
Yes. Hello.
You're not in presenting mode. I don't know if that will cause you a problem if you have any videos later.
Yes, I am in presenting mode on my screen here.
We're not seeing it. We're seeing the sort of editor, PowerPoint editor view.
Okay. Yeah.
Sorry.
Do I need to click something on the? Okay.
If you click on the top of your PowerPoint to start your presentation.
Yes.
Yeah.
Okay, I have done that now.
Oh, okay.
I was in presenter mode. Is presenter mode now or not?
No, we're still seeing your editor. Can I suggest you switch off the screen share and come back to just the window? Select the window when you. So switch the screen share back on and select the window.
Okay.
And then go to screen share, and then go to presenter mode. Sorry.
Select window. Okay. Entire screen. Okay. I think. Oi. Oops. Is it working now? Can you?
Yes, that's great. Sorry about that. Thank you.
Yeah, no, thank you. I don't know why this wasn't working. Okay, thank you for this delay. Okay, so the outline of my talk is I will talk about our work on combining atomic force microscopy with various kinds of fluorescence optical microscopy. And so I will focus today on the 2 system integrations that we have been working on over the last, almost decade. Well, not entirely, but almost. So I will talk today about integrating AFM with differential spinning disk microscopy and with SIM microscopy. So I would just like to briefly introduce you for maybe the members of the audience not so familiar with AFM. So we are working with liquid mode AFM, and so basically we use that to characterize topography, but also elasticity and stiffness of biomaterials. And so we aim to complement this with optical fluorescence microscopy in order to observe dynamic processes. So as you all know, fluorescence microscopy is mainly used for detecting fluorescent markers and provide molecular specificity in the samples that biologists look at. So basically our goal is to actually add more information that the microscope can provide by actually multiplexing the technology. So here is a little bit of an overview of the hybrid systems that have been reported. And so the main important ones are existing combinations with confocal laser scanning microscopy, such as in the group of Alsteins in Belgium or Daniel Muller at the ETH. Then you have experts combining AFM with FLIM technology, such as Pierre-Emmanuel Milly in Montpellier. Then there are integrations with turf microscopy, palm microscopy, and so also STED, as done in the group of Alberto Diaspro in Genoa. And also earlier reports have been made of integrating AFM with reflection interference contrast microscopy. And so I saw from the agenda today that Omer Wagner will add an interesting new addition to this wheel here. So I'm looking forward to his talk later on. So just for a brief introduction, so basically combining AFM with fluorescence microscopy. So basically the AFM performed in liquid media approaches the sample with a cantilever that is stuck to a silicon chip. And basically these cantilevers, they're basically very thin, long strips, so of around 100 micrometers, and the thickness of these strips is only half a micrometer. And so typically for liquid mode AFM, it is very recommendable, and almost everyone has a cantilever that has a certain gold layer incorporated, and that is used in order to sufficiently reflect the AFM laser operative laser light, which is typically in the 800s or 900s of nanometers, depending on the type of AFM you have. And so basically what is happening with a very sharp tip, with a tip radius of around 10 or even less nanometers, the AFM moves very slowly, depending on the type of AFM, over your sample in order to investigate the topography and the elasticity of the sample. So an integration with the fluorescence microscope setup looks kind of on paper very straightforward, but sometimes it is not, and it is for a variety of reasons. And so basically one of the key limitations that you have in combining AFM with a very popular confocal laser microscopy is the following. So basically, while the scanning of the confocal laser scanning is relatively fast, well, I put here 1 Hertz, but of course it depends on the type of CLSM that you have. But if you combine this with a regular liquid mode scanning AFM, where images typically take 20 seconds or longer to integrate, so basically you have an interaction of the fluorescence excitation light with the cantilever. And so it is well known in the liquid mode AFM community that basically people filter out the interactions of the fluorescence laser light with the cantilever because it's known to disturb the cantilever. So actually what happens is that basically you have several processes happening here. So basically the fluorescence excitation light typically is absorbed by the gold nanolayer on the AFM cantilever, and that induces heating as well as cantilever deflection. And so when this interaction of this fluorescence excitation light is non-constant, this deflection is basically too strong. And so basically then further issues that are occurring are incompatibility of the imaging mode with of the cellular imaging media, for example, with the AFM cantilever. So some of the buffers used in Palm or storm microscopy, they are incompatible with AFM imaging. And so basically, Lisa Hirvonen, now at the University of Western Australia, has been working on developing new buffer media in order to integrate Palm and storm microscopy with AFM. So another issue, of course, is the transfer of noise of camera fans or other moving parts of the microscope to the AFM, and that's a very problematic thing. So we have been working on that, and so now I will talk a bit about our DSD integration. So Philippa invited us to collaborate on an application note, and so you can find this one on the Oryx website. So I will not spend too much time here, but basically this is the system integration contrary to the confocal laser scanning microscopy with differential spinning disk setup, or that implements aperture correlation microscopy. I'm sure Mark Neal will explain more about this later on in the program of the conference. But basically, what is happening is, and what is so this is a way to obtain an optically sectioned image, similarly as a confocal laser scanning microscope, and it is done by projecting a grid onto the onto the sample plane. Okay, and so basically one collects a conjugate indicated by a C and a non-conjugate image, and through image manipulation and correlation of the two images, one can obtain a optically sectioned image. But for integration with an AFM, this particular configuration has a very beneficial feature, because basically, if you compare the interaction of the fluorescence excitation light of a CLSM with the AFM, that is a relatively non-linear process. So every second, more or less, the laser beam would interact with the AFM cantilever if you operate both systems at the same time. And so basically that would always have quite a lot of laser light hitting the AFM cantilever, causing heating and bending. While if you do the same integration with the DSD, it turns out that basically the amount of laser light absorbed by the cantilever is constant over time, because the illumination light is constant. From the point of view of the AFM cantilever. So this is the setup that we developed 5 years ago, more or less. So basically we have our laboratory that is underground, has a very low noise floor. And so we have the system set up also on an Iberian anti-vibration platform, which is extra to the thing, which is preventing noise vibrations of the under DSD to be transferred to the microscope body, and then actually inducing vibrations in the AFM image. So basically, we have done noise studies in it and the induced cantilever bending. So basically, the critical aspects to consider here are the C-mount connection with the microscope body, as well as the XY stage of the AFM system itself. So strangely enough, we noticed that by adjusting or tweaking the screws on the AFM stage and the connection with the microscope, that had a very strong impact on the vibration transfer to the AFM. And so what you could see here basically is a topography scan of the AFM of a mica surface. And so basically, when the DSD is on, so basically when you're acquiring with the fluorescence system, you have a very strong noise. Well, strong, the noise is 2 nanometers. For some samples, this might be acceptable, but for many that you would like to observe with an AFM, I would guess it's not. So basically, if you take a Fourier transform of this, you can see that there is a frequency peak here at 100 Hertz, which corresponds to this extra noise here. So when we switch off the system, we can do that. But so basically, we managed to get rid of this noise, and we managed to bring the vibration level. So when we do a scan with the DSD on and off, basically we can reduce the noise induced by the DSD to these 4 peaks here that you see, corresponding to a noise peak level of 75 picometers. So basically, there is a well-established connection between cantilever bending that is induced and the temperature increase that the bimorph would undergo. So the AFM cantilever are known as bimorphs, and so because they consist of a gold and a silicon nitride beam, and so basically if we illuminate with 560 nanometers with the DSD, illuminating around 170 microwatts, we observe an induction of around 9.1 nanometers of cantilever bending. So if you use a model developed by Timoshenko in the beginning of the 20th century, that would correspond to a temperature increase of around 0.33 degrees Celsius. So we can prevent this cantilever bending by using a different type of AFM cantilever, which is known as the QP Bio AC. So there, the gold is actually coated only at the extent of the thing. So in a matter of time, I will speed up a little bit. But so basically, we have also confirmed this analytical model here of the beginning of the 20th century by using FDTD simulations, and we have observed that the predictions of that relatively basic model are confirmed by FDTD simulations linked with a heat solver, and that we have performed in Numerical. So basically, what's the prediction of our numerical simulations? They kind of go as far as indicating that potentially using 1 milliwatt of confocal laser illumination, and if you would shine this onto an AFM cantilever, you could induce temperature increases up to 10 degrees. Basically here in the what we have done is we have also explored the quantitative imaging aspect of the AFM, which is basically for every pixel that the AFM records, we acquire a force curve, basically. So basically what happens here is the AFM approaches and pinches a lipid membrane, and then it basically you observe a sort of breakthrough force. And then also in the retraction phase of the AFM cantilever, basically you can monitor the adhesion force. And what we managed to do is we managed to overlap the adhesion force image with the fluorescent image acquired by the DSD. So we have also confirmed this on a bone cell population, whereby we had a mixed bone cell population, and we were observing which of the cells were stiffer compared to the others. So let me also now briefly talk a bit, but I think we're running a little bit out of time, I see. So we have also expanded our technology by integrating SIM microscopy with AFM. And so basically the same principle that we observed with integrating the DSD with the the AFM also applies to the SIM. So the SIM appears to be very gentle to the AFM. So basically in 2018 we organized a workshop sponsored by OSA where we demonstrated this setup. So basically we had a Nikon system integrated with JPK, which is now Bruker's system, and so here you see the overlap of the cells. So you have here the super resolved SIM image, whereby we overlap with the AFM, and so basically, very interestingly, we also noticed that we were able to do colocalized and simultaneous imaging of both the AFM and the SIM, which is I believe to be very interesting for potential dynamic investigations that we can do. So basically we noted that the fluorescence excitation light of the SIM has almost no impact on the AFM operation, and that's quite remarkable, because if people try to combine STED microscopy with AFM, what typically happens is that the images have to be taken very independently of each other, because the STED laser beam typically blows away the gold coating on the AFM cantilever and it destroys it. And so basically the same almost applies to STORM, but there some solutions have been found. But so basically what you see here is an overlapped image of whereby we create different images at different force levels of the system. So this is basically an image reporting on the fluorescent reporters, and at the same time the mechanical properties of the sample. So just to conclude, I believe that this is combining these techniques is very interesting, and there's still advances to be made. So especially it would be very interesting to combine SIM microscopy or DSD microscopy with high-speed AFM, because that would bring at least the acquisition rates of both systems in the same order of magnitude. And also we could also explore video rate SIM, which would then also allow to observe dynamical processes in greater detail. So yeah, these are the conclusions. We have combined AFM with DSD microscopy and with SIM microscopy. So we believe that these two systems are capable of simultaneous data capture, which is something that many others of the known integration system struggle with. So of course, turf microscopy, there it is possible it is very straightforward to do the simultaneous data collection, but then of course you're restricted to the bottom cell membrane if you use this technique. So I would like to thank my colleagues. So Katarina Mora has been working on the bone cell imaging, and Anna has worked on the sim integration in the past, and so Federico and Anna have worked with us to do the FDTD simulations. They are students from and a professor from University Nova in Lisboa. And so, and I'd like to thank my colleague Adelaide, who has been working with me over all the last years working on this technology. So thank you for your attention.
Thank you so much, Pieter. As you know, I'm fascinated by this correlative technique. So this is the first talk we've had so far that uses the Aurochs technology. In this case, a very, very old DSD-1 that was supplied by Andor back in the day. So yeah, obviously the images you could achieve nowadays would be much better, I think. But yeah, it's really cool the fact that the Aurochs spinning disk method is so useful for this by the even illumination of the cantilever and all those advantages. So I'm very excited about it. So we did have a quick question from Benjamin Shaw. He said, to stop the cantilever bending with respect to temperature, can you gold coat the other side to cancel out the stress? Ah, you're on mute.
Sorry. Well, this is an interesting question. Well, then one would have to make a trimorph, I presume, to cancel out the bending. That could maybe lead to other issues but it's an interesting thing. Maybe it could work out, but for sure it would not prevent the absorption of the fluorescence excitation light by the gold layer that actually then induces a temperature increase, which I think is something that people kind of have ignored until now, because liquid mode AFM actually to do dynamic investigation in liquids is incredibly hard because of the time it takes to acquire images. And so this is something that people now try to do by going to high-speed AFM technology. So I would say regarding the bending, that might be a potential solution, and thank you for the suggestion. But I think it would be very hard to implement, and you would have to speak to the companies making the AFM cantilevers to produce these things, which
Understood. Well, maybe you can catch up with Benjamin Shaw in the chat folder or offline and discuss the possibilities. And as Pieter said, feel free to look at our application note on our website, and it gives links to the publications that are out there to see if you're interested in doing the same technique.